Okay, hello. This is going to be a mini lecture on gravity, on apparent weight, and on orbits. So here's the first thing that we need to talk about with gravity. This is what we call the universal gravity down here. This is the magnet, how we calculate the universal gravitational force. So gravitational force is an interaction between two objects that have mass. And so this gravitational force is proportional to the product of their masses, m1 times n2, divided by the distance between their centers squared, and then we have to multiply it by this gravitational constant g. So that's the gravity. This is the same as mg. If you put in m1 as the mass of the Earth and r is the radius of the Earth, you get this whole stuff as 9.8 newtons per kilogram. Okay. So how do you determine g? Well, the first way was done by Cavendish a long time ago, and what he did was to take this rod. This rod right here it's about maybe, let's say it's half a meter long. It could be anything. And it has two small masses on there. And it's supported by a wire. And this allows, since it's supported by a wire in the middle, any small little push on the side will get it to twist. And the more it twists, the greater the torsion in here that prevents it from twisting. So what you do is you take these larger masses, put one right there and one right there. And then since these both have mass, there's a gravitational interaction between these two. But it's very, very small. And so but this is supported by a wire, so that small force can attract to this and get it to bend. So if you know the mass of these two objects and the distance between them, and then you can find the force by how much it twists, you can find everything but g and solve for g. And you get the gravitational constant is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. So it's not very large. And this gravitational force is a very weak force. Okay, so that's gravity. What about this? What about these guys in the International Space Station? There are girls in the space station too, but just not in this picture. So it looks like they're just floating around with no gravity. So let's talk about gravity, weight, and apparent weight. So why are these guys floating around? Let's do a quick calculation. Let's say I have an astronaut with a mass of 70 kilograms. The International Space Station orbits around 360 kilometers above the surface of the Earth. So I can calculate the gravitational force on the surface of the Earth and the gravitational force in orbit. So in orbit, obviously, they're further away, so they're going to have less gravitational force. So first, on the surface, I put in g, the gravitational constant, right there. I put in 70 kilograms for the mass. The mass of the Earth is 6 times 10 to the 24th kilograms. And then this is the radius of the Earth, 6.3 times 10 to the 6 meters. And you get 706 newtons. And you could convert that into pounds. It's 60 pounds. Now the same thing for in orbit. We still have g. We still have the mass of the person. We still have the mass of the Earth. But now we have the radius of the Earth plus this extra orbital distance, which is just 0.36 times 10 to the 6 meters. And you get 632 newtons, or 142 pounds. So, they're not weightless. This is the gravitational force. It's not zero. Okay. So, why are they floating around? Why do they feel weightless? That's where we're going to start with. Okay, here is a model I made. It's a model of a person. So think of a person as a series of masses connected by springs like this. And so this is a person standing on the surface of the Earth in an elevator. And so this top mass, this spring right here is compressed because gravitational force pulls down, so the spring has to be compressed to push up. And so that here's the net force on that mass. It's 9.8 newtons up, 9.8 newtons down, so net force is 0. Now the next mass down here, it compresses the spring down below it a little bit more because it has the spring pushing down on it, has gravity pulling down, and the other spring pushing up. So as you go down, the springs get compressed more and more. Okay, this blue arrow represents the total force on this person. Now over here I have a person in an elevator. The acceleration is 0, so the floor is pushing up and the Earth's pulling down. And the floor plus the earth equals 0. That should be a 0 vector. So these two forces have the same magnitude, but they're pointing in opposite directions. This is how you feel probably right now, because you're probably just sitting somewhere. Okay. Now, what if I take the elevator and I press the up button such that it accelerates up? So here's my person again. In order to accelerate up, I need a net force in the upwards direction. Well, gravity didn't change. You're the same height above the floor, the ground. So you still have the same force from the earth, but the floor has to push up more. It has to in order to have a net force up. And so in this case, the floor increased. And if you do this, you push an elevator, you feel a little bit heavier. Okay? So you feel heavier even though your weight didn't change. Here's that modeled in my little spring model. So now even the top mass, the spring gets compressed more in order to make a greater force pushing up so that it can accelerate. But all of them get compressed more. Okay, so this is accelerating up. You feel heavy, but your weight is the same. What if you accelerate down? Now you're moving up to floor number 8, and the elevator starts to slow down. So you're accelerating down. The only way you can do that is to have a net force down. Well, again, the gravitational force doesn't change because you're not really any further away from the Earth. So the floor has to push on you less. And you feel lighter. You've probably done this. Here's the model over here. You can see that this spring doesn't have to push down very much, push up very much on the top mass, which means that all of these springs below don't have to push up. There's less compression. So it's like your spine, okay? And you feel lighter. Now, what if the elevator was accelerating down at free fall? So someone cut the cable, which they should never do, because that's mean. Well, then you would free fall down, and there'd just be the gravitational force on you. And all of these springs, none of them would be compressed. And you would feel weightless. There is a gravitational force on you, but since each mass has the same gravitational force acting on it, there's no compression between these springs. There's no force of the floor push on you. There's no compression. And this is what we would call weightless. You can do this. They actually have rides like this. They have rides, I think I have a picture of that. Let's see. No, I don't. At where these things drop down and you feel weightless. Here's one other thing. What if I was far away from the Earth where there was no gravity? It turns out that actually, if I accelerate up, I can make these springs compress exactly as though you were standing on the surface of the Earth by accelerating up. And so, in this case, you would feel just like on Earth, but there's no gravity. Okay, so gravity is not what you feel. You feel this compression in your spine, all over your body, really. Okay, so an accelerating floor would make it feel just like you're standing on the surface of the Earth. Here's a picture inside a plane. This is a jet plane called the Comet. And this plane flies such that it has a vertical acceleration equal to 9.8 meters per second squared. So this is just like a falling elevator. And so the people inside have a gravitational force, but they are weightless. And it's called the Comet because you can only fly in this pattern for maybe 30 seconds. And then in order to not crash, you have to fly with a much higher acceleration, and this alternation of weightless and heavier and weightless and heavier, you throw up. Okay. So that's the weightlessness. So in space, you feel weightless because you're accelerating at the same value as gravity, and there's no normal force pushing on you, and so you feel weightless. But how do you accelerate when you're orbiting? So that's what we're going to look at now, gravity and orbits. And you can see the background change colors because that means it's a new thing. Okay, here's a sample. Here's a spacecraft, and it's moving in a circular orbit around the Earth. And the radius of that orbit is something like r. And there's the only thing acting on the spacecraft is a gravitational force pulling towards the center of the Earth. And as you get further away, you have a weaker and weaker gravitational force. So here's the gravitational force on the spacecraft. So the gravitational constant g, I use big M for the mass of the Earth, little m for the mass of the spacecraft, and r is the distance to the center of the Earth. The momentum principle says, actually, I should change this. The momentum principle says this is equal, this net force is the change in momentum over the change in time. And for an object moving in a circle, the change in momentum, the magnitude of this change in momentum is going to be mv squared over r, where here r is a distance to the center of the Earth. So this is true for anything moving in a circle, mv squared over r. And I could write that also, if I wanted to, as mr omega squared, if you want to deal with the angular velocity. But let's deal with this one like that. Okay, so now if I put this net force due to gravity up here, along with this change in momentum for something moving in a circle, I get the net force is just gravity, g m mass of the satellite over r squared, equals mv squared over r, and I can solve for v. So the first thing you know is the mass cancels. This little mass cancels. So the mass of the satellite doesn't, or the spacecraft doesn't matter. And then I have one of these r's cancel. So I get v squared equals gm over r, or v equals the square root of gm over r. So in order to move in a circular orbit, you would have to move this fast in order to have your change in momentum with respect to time be the same as that gravitational force. So the further you get away from the planet, the lower this velocity is you need to move in a circular orbit. Also, if you're moving too slow, you won't be in a circular orbit. You would kind of curve down and not be in a circular orbit. Okay, this is the solution for circular orbits only. Well, you know, this same idea applies to planets too. So if I use the same thing up here, v squared equals g m over r, well, now planets are orbiting the sun. So r is an orbital distance to the sun, and m is the mass of the sun, then v would be the velocity of the planets. So here are the planets, all 8 of them, because there's only 8 and 8 only. And if I plot the orbital speed versus 1 over r, and you can see up here again, orbital speed squared. Does that say squared? It should be squared. Versus 1 over r, then the slope of this should be gm. So this should, and you see all the planets fit this line just nicely. Well, what about the moon? Does the moon orbit the Earth or the sun? Right here, this is a tough problem because of this reason. I made this as a computer program, and this shows the sun, the Earth, and the moon. The Earth and the moon are, everything's correct size scale. And the Earth and the moon are the correct distance away from each other to scale. But the problem is, the sun's massively large. Look how I couldn't even fit it in the picture. Okay, so what happens when I try to represent all 3 of these with the Earth orbiting the sun and the moon orbiting the Earth? Typically, people draw a picture like this. This shows the Earth going around in a circular orbit around the sun, and then the moon going like this, orbiting this is actually, the moon is orbiting the Earth at a constant speed, but everything's scaled down, okay? And this says, well, it looks like the moon's not orbiting the sun. It looks like in some parts over here, the moon's bending away from the sun and has an acceleration towards the Earth, okay? But it's actually not true. Here's a correctly scaled, zoomed in picture of the Earth and the moon's orbit around the sun. So this line, it's top up here and then switches to the bottom, is the Earth going around the sun. The sun's not in the picture. And the top one's the moon. I mean, right here, it starts at the bottom and switches to the top. That's the moon. And so you can see that the moon does switch sides, but it's still curving towards the sun the whole time. Okay, so the moon does orbit both the sun and the moon. The sun and the Earth. It orbits both of them at the same time. Here's a better picture. This is the distance from the sun as a function of time, and you can see the moon and the Earth. Okay, and the Earth actually changes its distance because the moon pulls on it too. So it's actually not in a completely circular orbit. But the next picture is better. Next graph. This is the acceleration towards the Earth, the sun. And you'll see here the Earth is always accelerating towards the sun. And so is the moon. So the moon has greater and lesser accelerations, but it's always a positive value. It's always accelerating towards the sun. Okay, so the moon orbits both the Earth and the sun, but that other picture was wrong. Okay, so that's the basics of orbits. Oh, one other thing. Let me switch back here. What if I used this formula and I increased the distance, the orbital distance, until the angular rotation rate was 1 rotation per day? In that case, this would orbit the Earth at the same rate that the Earth spun. We call this a geosynchronous orbit. A geosynchronous orbit has the orbit rate as the same as the rotation of the Earth. If that orbit is also directly over the equator, it's called a geosynchronous orbit. A geostationary. A geostationary orbit is really nice because that satellite is in a location relative to the surface of the Earth that's the same position all the time. And so you can put a satellite there and you know exactly where it is. You can point your satellite dish towards it and you can communicate with it. And this is how we use satellite TV for one of the uses. And you'll notice all those satellite dishes point somewhere south because they're pointing towards the equator. That's where those geostationary orbits are. They're above the equator. But if you solve for this R, it actually is pretty far away. They're not in the region of the space station. If you do this for the space station, it only takes about 90 minutes for the space station to orbit the Earth. So that's it. I know it was fast, but I'll try to get it all in one video. So I'll post another gravity orbit video to help you along.